Alright, so the second type of double displacement reaction or double replacement reaction that we can have are called acid-base neutralization reactions. So you've still got the cation and the anion switching with each other. So A is now going to go with D anion and C is now going to go with the B anion. And what happens is that one of these is an acid, one of these is a base in the reactants, and they're going to combine to form water and a salt. So they're going to neutralize each other. So remember, you can recognize acids when the hydrogen is in the cation position, and you can recognize bases when the anion is the hydroxyl group. So you can see this is the acid, hydrochloric acid, and lithium hydroxide is going to be our base. And when these recombine, you can see that the H in the cation position here is going to swap positions, and it's going to go with the OH. This is going to form a molecule of water, so it would form HOH or H2O. So this is being converted from ionic forms into the liquid state of water, and now it's covalently linked together. This is very difficult to get to fall back apart. The lithium then is going to recombine with the chlorine to form lithium chloride, which is now a salt in aqueous solution. So as long as you add equal amounts of the acid and the base, they will neutralize each other and form lithium chloride and water. So this is an acid-base neutralization. They're probably the easiest type of reaction to recognize because you've got the acid and the base that you can visually see, and you've got water and salt as the components coming out. So these are fairly easy ones to recognize. So you can find acids and bases in many kinds of cleaning products or in products that we use for cooking or baking. And commonly for food molecules, they typically are more acidic than they are basic. And I think that's because our stomach is very acidic, and so we like to tend to eat things that have greater acidity rather than basicity that would neutralize the stomach acid. So, and you can see that if you mix certain cleaning compounds together, you're mixing these acid and base reactions, and they're actually pretty reactive when they're neutralizing each other. And so you don't want to do that because sometimes they can emit foul gases that can be kind of dangerous. So always be sure to check out and make sure that you can mix these different compounds together. So the next type of reaction that we're going to talk about are the oxidation reduction reactions or redox reactions. These guys are a little bit more difficult to recognize and to follow because the things that change are the electrons. So the oxidation state of the element is actually changing, and so sometimes these can be more difficult to actually visualize. So we're going to have some definitions that go along so that we can determine when something is being oxidized or when something is being reduced. So if you have reactions involving covalent compounds, if these are redox reactions, the electrons are going to be rearranged as the bonds are broken and new bonds are formed. So historically, the word oxidation referred to the combination of an element with oxygen, and reduction referred to the removal of oxygen from an oxide to yield the element. However, this is kind of an oversimplification because oxygen doesn't have to be involved in this process, but it's so common on the planet, and it does have so many reactions like this that cause the transfer of electrons that the whole process was named after the oxygen molecule. But other elements can also be involved in redox reactions. So today, the words have taken on a broader meaning. Oxidation refers to the loss of one or more electrons, while reduction refers to the gain of one or more electrons. So an oxidation-reduction reaction, or a redox reaction, is one in which the electrons are transferred from one atom to another. So if you are losing electrons, you becoming oxidized, you're going to become more positive, right? Because electrons are negatively charged, and if you lose them, then you would be less negative or more positive. So you can see the oxidation occurring in this atom, represented by A, it starts out being a -2 charge and it ends up being a -1 charge. So it is getting less negative, and so that means it's getting more positive. That means it's lost an electron. So you can see the transition here from a -1 to neutral charge. So it's lost another electron. Now it's neutral. If it loses another electron, it becomes positively charged because there's more protons than there are electrons now. And a +1 going to a +2 state, also an example of losing electrons. If we go back in the opposite direction, become more negative, this would indicate that we're gaining electrons and that we're going to be reduced. So there is a great mnemonic to help you remember which one is oxidation and which one is reduction. And that is Leo the lion says grr. So where Leo means if you lose electrons, you become oxidized. And if you gain electrons, you become reduced. So this is my favorite mnemonic for the whole 100 series. And in fact, I use it a lot even in my 450 level chemistry class. So this is an example of a redox reaction. And it's very common that you'll see redox reactions when you have elemental forms of metals that are reacting. So here we've got copper in its solid state, and it's going to react with the silver that is in its ionic state, in its aqueous. And so you can see we put the copper in its solid state. We put a copper wire in an aqueous silver solution where the silver is in its ionic state. You can see the copper is going to react with this solution, and it is going to give up electrons to that silver. So now the silver is becoming elemental, and it is going to a solid state, and so it's precipitating. So you can see the evidence of the silver precipitating out on top of the coil of copper that we initially put in there. So that's the silver that's precipitating out of solution. And you can see that the solution has taken on a blue color rather than the clear color, and that is the copper in its ionic form turns blue, and it becomes soluble in water. And so it is becoming soluble in this solution, trading places essentially with the silver. So the copper has lost electrons. It's gone from being 0 to +2. So this one is the one that loses electrons, and so it is the oxidized component. The silver is going from a positive charge to a neutral charge, so it's gaining electron. It's becoming more negative. And so as it gains electrons, it is becoming reduced. So it is the grr part of the equation. So we can see a similar situation here with the bromine and the iodine. The bromine is in its elemental form, and so it is neutrally charged. Anytime you see anything in its elemental form, remember, it has the same amount of electrons and protons, and so it has to be neutral. So bromine in its elemental state is neutral. Iodide is in its ionic state here, and so it's the anion, or 2I-1. And when this reacts with the bromine, it's going to actually lose electrons, and it's becoming neutral, right? So it's going from a negative state to a neutral state, so it has to lose those electrons. Since it's the one that's losing electrons, it's the oxidized component. It's Leo in this equation. The grr part of the equation is the bromine. The bromine's going from a 0 charge to a -1 charge. So it is becoming more negative. So as it becomes more negative, it does so by gaining electrons. And so it goes from being in the elemental form of Br2 to the anionic form of Br negative. So oxidation and reduction reactions always have to happen together. When one substance loses an electron, it is oxidized, and then the other substance has to gain the electron and be reduced. You can't just randomly lose electrons and have them go nowhere. They always go to something. So we can say that the substance that gives up an electron and it's becoming oxidized, right? If you lose an electron, you're oxidized. And it causes the reduction of something else. It can be called a reducing agent. So a reducing agent is something that will reduce something else, and so it's going to give an electron to something else. So the thing that gets oxidized reduces something else and is called a reducing agent. The substance that gains the electron and causes the oxidation is called an oxidizing reagent. So the thing that gets reduced oxidizes something else. So the oxidizing agent is the GR part of the equation, and the reducing agent is the LEO part of the equation. So I know these are kind of confusing at first, but once you start working with problems, it'll start making more sense, and we'll get some practice recognizing redox reactions. So our reducing agent is going to be the thing that undergoes oxidation, the thing that loses one or more electrons. This is LEO. It becomes more positive or less negative. It's going to lose the electrons. And it also may gain oxygen atoms in the process, which can help you identify the thing that's getting oxidized. So the thing that gets oxidized can act as a reducing agent on something else. The oxidizing agent is going to oxidize the reducing agent, and it's going to gain one or more electrons. So it causes oxidation, and it itself undergoes reduction. So this is the GR part of the equation. It's going to become more negative because it's gained those electrons. It also may lose oxygen in this process, and so that's one way that you can recognize if you have a redox reaction going on, is watching if oxygen is moving from one compound to another. So reactions of metal with water or with acid is particularly important processes. So alkali metals, for example, and the alkaline earth metals are the most powerful reducing agents, and we said that these guys are very, very reactive when you put them in pure water. So if you put an alkali metal like lithium or sodium or cesium into water, it actually explodes during that process of reacting and oxidizing with the water. So it's acting as a reducing agent, which means it's going to get oxidized in the process. It's going to be the LEO part of the equation. It's going to lose electrons. And that makes sense, right? Because our alkali metals want to lose one electron and become a +1 state so that they can reach their octet in the noble gas electron configuration. So our reactive nonmetals then are going to be powerful oxidizing agents. They're going to be able to rip off that electron from another molecule. They have the highest oxidation energies. They also have the highest electronegativity because they are attracted to the electrons. They want to grab them and gain them. So they have the most favorable electron affinity or the highest electronegativity values on the table. So in our reactions then involving metals and nonmetals, metals tend to lose their electrons, just like we learned with ionic bonding, and the nonmetals tend to gain the electrons. And the reactions that go on to form ionic bonds are redox reactions. So the number of electrons lost or gained can often be predicted then based on the position of the elements in the periodic table. And you've already had lots of experience doing this with building our ionic bonds. In the reactions that involve nonmetals, the more metallic the element, the farther down and to the left in the periodic table, these guys tend to lose the electrons and become the oxidized component. And the ones that are closer to fluorine in the nonmetal category, these guys tend to be the oxidizing agents. These guys have more attraction for the electrons and want to gain them. So they themselves are going to get reduced in the process. So they are less metallic of our nonmetals. So a good example of a redox reaction is a battery cell. So when the battery cell is hooked up, you can see that we actually are generating electricity from our battery cell, and so we're actually popping off electrons, and we're popping them off of the zinc on this side here. We pop them off and we run them through our circuit, and so we're running our toothbrush in this case, so our battery operated toothbrush. The electrons get sent back to the negative lead in the battery, and they're given to the magnesium oxide. So this guy is going to gain the electrons, and it's becoming reduced then, and it's going to send those electrons in the form of the hydroxide ion over to the zinc. And so it kind of restores this potential as it goes through the battery. So we'll talk about some different types of redox reactions in the next section.